This is the video for question 19, 20, and 21. If you only got one or two of them wrong, sorry, you're stuck watching the whole video anyway, but maybe you'll learn something. So the basic idea for all three of these is to think about the slopes of tangent lines and actually compare the instantaneous rates of change to different points of x. And the second major concept is that linear approximation is only an estimate, and care must be taken in order to choose a value of x that is relatively close in terms of the value of the function to the values being estimated. So let's look at this first. Which of the following values is smallest? So we want the derivative at 2. So that looks like it'd be about there, something like that. So it's going to be the slope of this line here. Then it says the derivative at 0.-9. So that's probably right about here, and that looks like it would be something like that. So if we're looking for the smallest, this is smaller than that one for sure in terms of slope. Now the derivative at 0, we know that from our optimization problems that the derivative at 0 is just about 0. It looks like it's maybe a little bit more, depending. Okay, and the second derivative at 1. Well, here's 1, and the second derivative actually is not looking at the slope of the line at that point, although the slope of that line would be negative anyway, so that would be the smallest, but the concavity is also negative. So the answer for the first one there is D, because that is the smallest, it's the only one that's negative. You can see all three of these are negative. Now, which of the following values is largest? Again, we're looking at the derivative at 2, the derivative at -0.9, the derivative at 0, and the concavity at -1. Well, since we want the smallest, it looks like if we compare the concavity here, or if this should be the first derivative, then these are both going to be more negative than this one at -0.9. Actually, no, the one at -0.9 looks to be the biggest, so that must be the answer. So that would be the most, oh no, that's positive. My bad. It would be this one because, oh wait, no, which one is? The largest is this one here. I lost track of what I was doing. So that is the largest slope because you can see that this one's negative, these two are positive, so the largest is going to be there. Now, suppose we want to estimate f of 1.5. So what we're going to do is take linear approximations to the function. Well, let's look at what that would look like at 1 and 2. At 1, it's going to be about here. And if we take a linear approximation, it would be something like that. And then at 2, as we know, it would be this. So given that, let's say this is about 1, and this is about 1.5, it's equidistant between 1 and 2. But clearly, the approximation at 1, it has a negative slope, just like the function. So this is the one at x equals 1 is clearly the better choice.